Welcome back, my friends, to the CTO Demon channel. Now, today, I'm sorry, it's going to be a difficult talk. We are actually going to explain why the algorithm for 3D fluoroscopic wiring works. And this is rather complicated. I have a headache when I think about it. But let me see if I can make it clear with some slides and with some illustrations. So the model we're using is the 24-wire position clock face model. In this model, we draw a clock face, and at each hour, 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, the wire can either be near the outer side of the vessel or near the center side of the vessel. So in this first instance, let's assume that the target, the distal target, is slap bang in the middle of the clock. Okay? Now, let's take our two fluoroscopic angles as 4 o'clock and 7 o'clock. From now on, we'll refer to camera 4 and camera 7. Now, if we have this arrangement, as you can see, there are two lines where the wire, if the wire is in that position, the distance from the wire to the distal cap is going to be equal in the 4 o'clock and the 7 o'clock camera, in the IV and the PV camera. Okay? And these two lines run from 2:30 to 8:30 and from 11:30 to 5:30. Any wire on these two lines will be equal distance in the two views between 4 and 7 o'clock cameras. Okay, so if we color it in, what we have is everything in green is the wire is further in camera 7 than camera 4. And everything in yellow, the wire is further in camera 4 than in camera 7. In other words, when we do our first wire rotation, what we end up is this, where everything in the yellow, the arrows point towards the center, and everything in the green, the wire points towards the center. Now, this is what we will end up with when we do the first rotation of the wire, pointing the wire towards the target at the view where the wire is furthest from the distal cap. In camera 4 in the yellow segments, and in camera 7 in the green segments. Now, of course, what really happens is the wire could be in one of three positions, because although we see in camera 4 is pointing towards the target, it's not slap bang straight. Sometimes it may be a little bit this way, a little bit that way. So like the wire point in 1 o'clock, it could be in one of three directions roughly. I mean, it could be infinite directions, but at most this kind of angle. Okay, so that's why when we go to the other view, we need to straighten the wire tip so that the wire remains in one position and our angle of turn is accurate. So we said the rotation, if it's the same distance between the two views, we rotate 44 degrees. If it's half the distance in the second view, 22 degrees. If it's a quarter distance, 11 degrees. And this is the diagram that illustrates why that works. So if the wire is slap bang in the middle, like 1 o'clock, okay, and we straighten the tip, then it's already pointing towards it. So we don't need to rotate the wire at all anymore. We just go back to the 4 o'clock camera and puncture. If it's on an equipoise distance line, like the 230 outer dot wire in this diagram, then we need to rotate it 44 degrees. And you can see 44 degrees is going to put it pointing directly at the target. If it is like this outer point 2 o'clock wire, okay, so you can count it roughly on the 4 o'clock camera, okay, moving towards that 2 o'clock outer is around 6 minutes, okay, the distance. At the 7 o'clock, okay, it's around 1.5 minutes, 2 minutes, right? 1.5 to 2 minutes. So it's about a third, okay? So you rotate 33 degrees, okay? So you can see how after you rotate this, the wires are going to then point towards the distal cap. Now, let's make it more complicated. On the same clock face model, now the distal target is not in the middle of the clock, it's at 7:30 on the outer edge. And our camera is now 6 and 9 o'clock. What will happen? Well, very simply, the equipoise line is between 1:30 and 7:30. Everything in the green, the wire is further in camera 6. Everything in yellow, the wire is further in camera 9. And so if we do the directing of the wire towards the target, this is what we get. Everything in green is going to point towards 9 o'clock. Everything in yellow is going to point towards 6 o'clock. Okay. Of course, granted, it's going to be a little bit off sometimes. So if we go to the other camera and we straighten the tip, this is the wire position we're going to have in these 24 wire positions. Now, again, you can understand why the rotation works. If the wire is on the equal poise at 130 on the outside, okay, we need to turn 44 degrees to point it towards the target. If the wire is, for example, this 11 o'clock closer to the center position, okay, so on the 6 o'clock is around 2 minutes, on the 9 o'clock is around 1 minute, then we need to turn around 22 degrees. Okay, sorry, I got it wrong. 6 o'clock is around 1 minute, 9 o'clock is around 2 minutes distance. So you need to turn about halfway, 22 degrees, and you point towards the target. Okay, so you can see how this works out. If you turn it, then it's going to face towards the distal cap. We'll make things more complicated. The same arrangement around at 8 o'clock, outer edge distal true lumen target. The camera is now 11 and 2 o'clock. The equal poise line is from 11 to 8 o'clock and 8 o'clock to 5 o'clock. The green area, the wire is further in camera 11, and the yellow area, the wire is further in camera 2. Okay? So again, when we point the wires, all the green area is going to point towards 8 o'clock, and so is the yellow area is pointing towards 8 o'clock inwards. Okay, and again, we can straighten, and you can see the same principle works perfectly well. If you're on an equal poise line, like 6 o'clock outer side wire, okay, then you need to turn 44 degrees. If you're on a 3 o'clock outer side wire, then you're turning around 11 degrees, okay, because the length from 2 o'clock to 3 o'clock in camera 2 is around 1, compared to the length from about 8 o'clock to 1 o'clock is about 4. So it's about a quarter. So you turn 11 degrees and you'll be pointing towards the target. Now, I hope the clock face is not too complicated and we managed to get on top of that. But it's not something that you have to understand. It's something that just helps explain why this algorithm works in principle, in theory, okay? So the other principle is talking about, well, if you turn to the initial view and you try to wire this cap, sometimes it goes too near side, sometimes it goes too far side. How can we correct this? Now, I did a little video with an airplane thing, which was not as neat. So I'm doing it with slides. So ideally, imagine you're flying a plane and you're trying to drop a bomb on a tower, okay? So the bomb should fall and drop straight onto the tower. But sometimes the bomb falls too quickly and it drops to the near side of the tower. How can you correct this? You fly the next round, you fly the plane higher, which means you pull the wire back further. With a further distance, the wire has more distance to travel towards the target. Now, sometimes you can get towards the distal cap and be slap bang on the distal cap tip and can't puncture in. This is because the wire is slipping off. Now, that's another problem. That is the tough distal cap problem, which has been addressed in the HLC paper published previously on our wiring. And another video has talked about it, and that we need to step up with a high penetration force wire, because just changing the position is not going to help. But assuming the wire you have in hand is enough to penetrate the distal cap, then by coming back more proximally, you can direct it to the tip of the distal cap and puncture in. And if the wire goes too far the other side, well, this is easy because this wire is torqueable. You can turn it, and you know the current direction is 180 degrees from the correct direction if you're too far. What you do is you pull back to where the wire is just above the distal cap, and you turn 180 degrees and you try to puncture in, because when you turn 180 degrees, the wire is going to start deflecting the opposite direction. So that will be the way to deal with if you've gone too far from the distal cap. So the conclusion is, no matter where the target is in the vessel and no matter where the X-ray tube is relative to target, as long as we have a 90-degree angle between the two views, we can use our algorithm to get 3D fluoroscopic wiring to puncture the distal cap. So I hope these principles and ideas are useful for you, and I hope you try it out. I think the mid-RCA, the mid-distal LED are fantastic pots to try it out. Actually, I first started doing this for mid-RCA CTOs, and now also some distal, mid, and distal LED CTOs where the distal cap is in the mid and distal LED, and it's fantastic. Distal RCA can work. Also, proximal RCA, proximal LED works fairly well too. It's a bit of a struggle to get the angles. You really have to push your radiographer or your fellow or yourself, if you're moving the table yourself, to get to those deep angles. But it does make a big difference to your distal cap wiring, both in terms of success and in terms of time. You do spend a little bit more time getting the angles, but when you do it, your success is much higher. And I would advise practicing this and trying it out, maybe on a mid RCA case is easier first, and then in the mid LED case, which is not too hard, and then you can try at different places when you come to those CTOs. So I wish you all the best luck when you try your CTOs, and I'm going off to Japan to meet with Dr. Okumura to try to work this through more detail, and hopefully there might be another video coming from Japan with Okumura Sensei that can make this even more useful for you. The best of luck to your CTO adventures, and I look forward to seeing you the next time. Do subscribe and press the like button if you like the channel and want to follow on. Bye-bye for now.